Okay, what we're looking at now is a short segment of a glycogen molecule, and we'll go over the structure of this momentarily, but just as a reminder, glycogen is the major storage form of glucose in mammals. It is essential for maintaining life. It's the major source of energy during prolonged vigorous exercise, and finally, it maintains blood glucose levels during fasting and starvation. The largest deposits are found in liver and muscle, and what we have is a backbone of alpha, in this position, 1,4 linked glucose units with alpha 1,6 branch points. Okay. So there are alpha 1,6 branches about every 10 to 12 glucose units in a full glycogen molecule. These molecules can contain thousands of glucose residues. There are far more non-reducing ends than reducing ends. Why is that? Because these non-reducing ends serve as the primary access points for the synthesis and breakdown of the glycogen molecule. So this highly branched nature of that glycogen maximizes the number of non-reducing ends versus reducing ends. So this is just a flow chart of the synthesis of glycogen and the degradation of glycogen. So technically, we can call the synthesis glyconeogenesis and the breakdown as glycogenolysis. And we're going to go through each side of this. So glycogen degradation is actually thermodynamically favorable. It does not require energy, but of course synthesis, like any other anabolic process, requires the input of free energy. Thus these opposing pathways use different sets of enzymes so that each process can be thermodynamically favorable under cellular conditions. And let's take a look at glucose or the glycogen formation. We start with glucose 6-phosphate, which gets converted to glucose 1-phosphate by phosphoglucomutase. We require this high energy molecule UTP, just like an ATP, only with uridine. The enzyme UDP glucose pyrophosphorylase hydrolyzes 2 phosphates, which are then converted to 2 inorganic phosphate molecules, resulting in UDP glucose. That UDP is then cleaved by glycogen synthase, and there's a branching enzyme that adds that glucose unit onto an existing glycogen molecule. Glycogenolysis, on the other hand, we are going to require a debranching molecule or debranching enzyme, some inorganic phosphate to phosphorylate by the glycogen unit. Glycogen phosphorylase is then going to add that inorganic phosphate and produce glucose 1-phosphate. So let's take a look at these just a little bit closer. This is what we call a branch point. So this is that alpha 1,6 branch. And digestion of glycogen can occur both in the GI tract or the tissue. So when we do ingest dietary substances that contain glycogen, we do have to begin breaking that down in order to utilize the glucose that's contained there. So we do have, we do have an enzyme in saliva. It's an amylase, and that is responsible for helping break down glycogen molecules, or at least to begin. But In the tissue, we are going to have a debranching enzyme, and that basically transfers what we call a limit branch. It's going to be a 3 residue unit of glucose or glycogen to the non-reducing end. And subsequently, we'll start cleaving glucose molecules from this basic backbone here. So repetition of this process results in the complete degradation of the polysaccharide into glucose units. So again, here is a branch. We have the non-reducing end. We're going to have phosphorylation of that non-reducing end, and then a cleavage. Glycogen phosphorylase is going to phosphorylate or add that phosphate molecule to that non-reducing end, and we will finally have that cleavage. Glycogen synthesis, on the other hand, we've looked at just in that original flow chart of both processes. We have a glucose 1-phosphate that is enters and it gets linked to our UDP. We're going to lose 2 of those phosphates, which are then converted to inorganic phosphates and then produce that UDP glucose. The synthase or glycogen synthase reaction is then going to remove that UDP and then add that glucose unit to a growing glycogen chain. The use of glucose rather than UDP glucose is unfavorable because it would be the reverse of a hydrolysis reaction. So we have to make that adjustment with the UDP here. Now let's take a look at how insulin affects these processes or the metabolism in general. So insulin is secreted when we take in glucose. Okay, so we've got, these are kind of high energy, or shouldn't say high energy, high glucose concentrations. So insulin is going to signal our cells to run glycolysis, run glycogen synthesis, lipid synthesis, and protein synthesis. Okay, these are all pathways that require energy. And if we've got high blood sugar, insulin is going to trigger our system or our pathways to utilize that. Now, we have high glucose, so we don't want to run gluconeogenesis. We don't need that, and we do not need to break down lipids either, because that will only produce more energy for us. We'll be taking a look at lipid catabolism and synthesis in the near future. So this is another slide I put together that I think I paused that and forget where I was. So this is a figure that I've put together that hopefully can help you visualize the big picture. We know under conditions where we have high glucose, we are going to store some of that as glycogen. So we would be synthesizing glycogen. However, hormones also play an important role, not only in the regulation of glycogen metabolism, but also the control of other metabolic processes. But we're going to look right now at glycogen control. So we're looking at two hormones, epinephrine and glucagon. Epinephrine or adrenaline, when it is secreted into the blood or increased concentrations are in the blood, it triggers that fight or flight response. Okay, so that activates this second messenger cyclic AMP. So if we have our fight or flight response going on, we do not want to synthesize glycogen. We want to break it down so we have increased concentrations of glucose in our blood. So epinephrine is going to activate cyclic AMP, which binds to protein kinase A. This is a kinase. It phosphorylates. Okay. So this is going to inactivate glycogen synthase. So this is a covalent modification. We phosphorylate that enzyme, and that will inactivate glycogen synthase. So this is its inactivated state. Conversely, this enzyme, phosphorylase kinase, is inactive unless it's phosphorylated. So protein kinase A phosphorylates phosphorylase kinase, and we get the active phosphorylase kinase in this phosphorylated state, which then in turn activates glycogen phosphorylase B, and we start degrading glycogen. So now let's take a look at glucagon. This is another hormone, and it's basically responsible for the long-term maintenance of blood glucose. So when blood glucose levels are low in between feedings, this also is going to turn off glycogen synthesis and activate glycogen degradation.